The Sudoedit vulnerability CVE-2021-3156 is a vulnerability that affected Sudo, a tool that is included in many Unix operating systems. It was introduced over 10 years ago and affected many versions of Sudo. This vulnerability was discovered by researchers by reviewing code, which is not necessarily a novel approach but does show that a simple mistake could lead to arbitrary privileged code execution. The vulnerability, as the title suggests, involves a heap overflow to manipulate other structs in heap. Here's how the code works using Sudo version 1.8.31p2. The biggest vulnerability comes from the set command function in sudoers.c. When sudo mode is set to either shell or login shell, the function will take the user argument and copy the string into heap. In this part of the code, if there are user args, it will add up the size of the string for each argument. Then it will use malloc to allocate an appropriate size. Then in line 865, it will start incrementing character by character and copying each character from the argument into user args. However, the problem arises here. If the character it sees is a backslash, it will increment the pointer forward one character and copy the next character. This would theoretically be desirable to escape certain characters. However, if the argument ended in a backslash, it will then copy over the null byte of where the string should originally end and continue on. Since the code doesn't stop at string length and only stops when from is null, it will continue copying all other characters it sees until it stops at the next non-escape null. As you can see, this allows the attacker to fully manipulate the overflow and the size of the malloc that is allocated for the user's heap. Now you'll be thinking, this seems like it should have been caught immediately. That is because when sudo runs, it runs the function parseArgs, which will check for all meta characters and add a backslash in front of it. Therefore, our input arg would go from this to this. Now when set command runs, it will increment the pointer past the first backslash, then copy the inputted backslash and stop at the null. Looking back at parseArgs and set command, we can see that the flags do not match. So how do we eventually get to set command with the flags mode shell but not mode run? It turns out when running sudo with sudoedit -s, the code sets the flag to mode shell and not mode run. We can therefore run the following command and get a core dump. There are checks to see that the heap has been manipulated and the program crashes. From here, the approach to the exploitation is quite free because the heap is at our mercy. The size that malloc actually allocates is determined by the attacker, and the buffer overflow is fully under the control of the attacker. Also, a great bonus is that this code allows the attacker to copy null bytes into the following overflow without the string copy prematurely stopping. The researchers explained 3 approaches of exploitation of the heap overflow. I will detail the approach using NSS. NSS, or Name Service Switch, is a function that retrieves data from databases like passwords or from LDAP servers. In this case with sudo, it is used to make sure that the user is properly authenticated to use the command by checking ets passwd or ets shadow. By using the heap, malloc, and free behavior to our advantage, we can manipulate certain environment LC variables to create holes in the heap to place the user arg's buffer. Since set locale starts at the beginning of the code, it will malloc and free environment variables at the start of the heap segment for sudo. Then by manipulating the size of the environment variables and the size of user args, you will be able to place user args into the hole created by free and place it in a position we want. Going back to NSS, the NSS load library function is used in context of sudo. Normally, it would be loading proper libraries that are needed. If you look at line 340, you can see that if service user ni library is null, it will attempt to load the library defined in the variable ni name. However, by overflowing into NSS service user struct, we can manipulate the data for the values that are in that struct. Because our overflow is so handy, we can place nulls into our exploit string and override the necessary variables in the service user ni struct and replace the variables with nulls and set the name of the library to load the path where we have our malicious code. Looking back at NSSwitch, we can see in lines 363 to 367 that ni name is sandwiched between libnss underscore and .so. This means our name variable must be set to something slash something, which will load the library of libnss underscore something slash something .so.2. Here, something.so.2 will be our malicious code which we run as root, since sudo will run as root. Although our approach may not be entirely novel, by reviewing code and using execution of the code against itself, we are able to use a simple buffer overflow to get a completely different program to execute in a user-controlled location. The greatest part of this exploit, again, is that any number of null bytes can be copied into heap by just escaping it with a backslash. Now we pivot into our demo. We are now in Ubuntu 2004. It is an older version of Ubuntu that still has the Sudoedit vulnerability. We can test this by running Sudoedit -s and ending with a black backslash. You can see that the core dumped. This shows that the current version of sudo is vulnerable. The exploit I will demonstrate is from Live Overflow on GitHub. The way the exploit is run is by running sudo m2 from the Python script. Inside sudo m2, we can see a simple script to run Sudoedit. All this does is it takes arguments given to it, it runs execve and passes the args as the environment variables. Looking at the Python code, you can see that once the string is being read into user args from set command mentioned earlier, we can fill the heap with arbitrary chars until we get to where the service user ni struct is. Then by passing in backslashes, we can input nulls in the appropriate places. Then we can pass in the name of the file with the malicious code. Note the name is xxxx/liveoverflow. The name can be changed to anything as long as there is a folder named libnss_xxxx and the file with the same name .so.2. The tz environment variable is used earlier in setlocale to manipulate the heap malloc and free behavior also mentioned earlier. Now looking in our libnss_xxxx folder, you can find the liveoverflow.so.2 file that completes the file name path libnss_xxxx/xxxx.so.2. The liveoverflow.so.2 is a compiled binary, and looking at the code that generated that binary, we can see that we are doing something very similar to what we did in class. The setup function is something done for shared libraries, and we just set the effective user ID and run /bin/bash. Let's run the exploit. And there you have it. A root shell on any Ubuntu system using the old sudo version run by any unprivileged users. So how do we defend against such attacks? First, code review is paramount. Looking back at the mismatching flags in sudo, it is clear that set command is not a safe function, especially in the way they assumed that parse args is to be trusted, and therefore going ahead with copying the string character by character. Second, there are tools like AFL++ that can randomize inputs for both files and arguments and discover crashes and potential vulnerabilities. Thank you for watching my presentation on the Sudoedit vulnerability.